We are in Chapter 1, Functions, Graphs, and Limits, Part 1. Material presented in sections 1 through 4 in Chapter 1, also in A.1 and A.2, are considered material already mastered. These notes provide a brief outline of the key concepts for these sections. And if you have any difficulties with the material presented in these sections, I encourage you to sign up for the free marks or the ASAC tutoring centers at Mount SAC. You can also talk to me about these more in depth if you need extra help. So the first section that we have is back in the appendix. It's A.1. It's a brief review of algebra. And the first thing we're going to look at is exponent rules. So problems with exponents can usually be simplified using a handful of exponent properties. Exponents represent repeated multiplication of a base. We will now attempt to derive some of these exponential properties. The first property that we have is y to the fourth times y to the second, which is the example for this property. And y to the fourth means that we have 4 y's. And y to the fourth means that you're multiplying those bases all together. And then we also have times y to the second, so 2 y's. And so this works out to be in a total of 6 y's. And so this would work for any other exponent that we would have. So in general, we can say it's going to be y to the a times y to the b is going to equal y to the a plus b. And so you would add those exponents. So we have an example right below, and it says x times x to the fourth times x third. And x doesn't have an exponent, so it technically has an exponent of 1. And so adding up all these exponents, since the bases are all the same, they all have the base of x, we're going to have 1 plus 4 plus 3, or x to the 8th power. The second example, part B, says 3x times 4x squared, and the numbers that we have are just 3 times 4, or 12. And then we have x, since this is the same base for both of these terms, and it's x to the first times x to the second, or x to the third, which again we get by adding those exponents together. And then the next one we have has both bases x and y in it. So we have x to the second, y to the fourth, times x, y to the second. And so just looking at those x terms, again, that x without an exponent is going to be x to the first. So we're going to have x to the third, y to the, and then 4 plus 2 would be 6. And so again, combining the y terms together. The next property that we're going to try to derive is going to be the example y squared to the third. And so y squared to the third means that we're going to write y squared 3 times. And from the property right up above, we know that y squared times y squared times y squared, and adding those exponents together would be y to the 6th. So in general, we would be able to say power of a power rule for exponents would be y to the a to the b, which is going to be y to the a times b. And likewise, if we have 2xy cubed, that means we would have to write 2xy 3 times. And you notice this time our base is not just a single variable, it has 2 variables and a number. And so from here we have 2 times 2 times 2, or 8. And then it's going to be x to the third, y to the third. So the power of a product rule of exponents, when you're multiplying 2 or more things together as our base, raised to a power, we'll say power a, would be x to the a, y to the a. And so the example right below says evaluate x to the third squared, and so we'd multiply those exponents together and get x to the 6th. For b, it's 2ab to the 4th power, so we're going to have 2 to the 4th power, a to the 4th power, and b to the 4th power, or 16, a to the 4th, b to the 4th. And then the next one that we have is c, which is negative 4x squared y cubed z, all raised to the 3rd power. So we're going to have negative 4 to the 3rd, x to the, and it's 2 times 3, or 6, y to the 3 times 3, or 9, and z to the 3rd. And then negative 4 to the 3rd is going to become negative 64, x to the 6th, y to the 9th, and z to the 3rd. The next property that we're going to try to derive from this example of 2 over y to the 3rd is going to be the power of a quotient rule. And so we have 2 over y times 2 over y times 2 over y. Writing that 3 times since that's what our exponent is. And so 2 times 2 times 2 is 8 over y to the third. And so in general, the power of a quotient rule is going to be x over y raised to the 8th power is going to be x to the a over y to the a. And so on the next page, we have some examples. The first one is x over 3 to the third, or x to the third over 3 to the third, which is 27. B is x y to the third over 4 raised to the second power. So we're going to have x to the second, y to the sixth over 4 squared, which is 16. Part C, we have to raise everything to that 5th power. So 2 to the 5th is 32. And then we have x to the 4th times the 5th power, which would be x to the 20th. And then we have z to the 5th times that 5th power. We would have z to the 25th power all over y to the 5th. So this rule only works when you're multiplying or dividing things inside those parentheses. It does not work if you're adding or subtracting, and you can see that in the example right below. So it says, does 2 plus 3 squared equal 2 squared plus 3 squared, as if you're distributing that exponent to both of those terms. And so you can see this by checking 2 plus 3 is 5, 5 squared, and then working out the other side, we would have 4 plus 9. 5 squared we know is 25, and then 4 plus 9 is 16, and you'll notice that those are not equal to, so no. This is an error, and so this is something to be very careful of. The next rule we have is a 0 power rule of exponents. And what this says is y to the 0, or anything raised to the 0 power, would just be equal to 1. The only thing that cannot be a base would be 0. And so we ask, why does this work? So the first thing is, if you had x over x, we know that this would be equal to 1. And we will see in a moment that when you're dividing, you actually are going to be subtracting your exponents. And so this is the same as 1 minus 1, or x to the 0 power. And so we can say that this is equal to 1. So using this property, we're going to have negative 5 to the 0. Careful thing on this one is that it is not negative 5 in parentheses. It's like negative 1 times 5 to the 0. And so from order of operations, we would do the exponent first. And so we have negative 1 times 5 to the 0 is just 1. So that works out to be negative 1. This is different if the negative 5 was in parentheses and that whole thing was the base. For the second one we have 7 to the 0, which is just 1, times. And this time we have negative 4 in parentheses raised to the second power. So this means negative 4 times negative 4, or positive 16. And so 1 times 16 would just be equal to 16. For part C, we have numbers and we also have variables. So multiplying those numbers together, we have 3 times 2 times 5, or 6 times 5, which is 30. And then x to the 0 here is just going to be equal to 1. And then we have x to the 4th times x to the 2nd, which we get by adding our exponents together. So right below this, we have rules of negative exponents. So a to the negative n is going to become 1 over a to the nth power, and that exponent is now positive. Likewise, if we have a negative exponent in the denominator, this is going to move to the numerator. And then if we have the third one, which is a over b raised to the negative n, what's going to happen is we would have a to the negative n over b to the negative n. And then we know that our b values have a negative exponent, and they are going to move to the numerator. And then a has a negative exponent also, and it's going to move to the denominator. So this is also the same as b over a raised to the positive n. And you can look at the two of those bases and see the difference. So the examples right below, the first one that we have is 11 to the negative second, which is the same as 1 over 11 to the positive second, or 1 over 121. And then for the next one, we have 4 over 3 raised to the negative first, which would be the reciprocal of this. So 3 over 4 raised to the positive first, or just 3 over 4. And then part C, we have negative 5 to the negative third. And so again, that negative is not inside the base. So it's like negative 1 times 5 to the negative third, or negative 1 times 1 over 5 to the third, which is going to be negative 1 over 125. So at the top of page 3, we have another property that we're going to derive, which is the quotient rule for our exponents. And so we have y to the fifth, which again we would write y 5 times with multiplication dots in between them, and then y to the second in the denominator. We can reduce these y's. Y over y is just 1. Again, another set, y over y is just 1. And we're left with y times y times y, or y to the third power. And so writing this in general, we can say y to the a over y to the b is going to be y to the a minus b, which is what we got up above. 5 minus 2 is equal to 3. And so we have an example right below that says 3 to the fourth over 3. And so that's 3 to the first. And so subtracting this, we would have 4 minus 1 is going to be 3 to the third, which works out to being 27. For the next one, for b, you'll notice that you have a 1/4 with our numbers. So I'll just write that out in front. If you can simplify any of those fractions, make sure you do that. And then we have x to the, in our numerator, exponent is a 1. And we have to subtract the denominator 1, which is a 5. And then for the y values, we have y to the third minus 1. And so this is going to be 1/4 x to the negative fourth y to the second, which works out to being y to the second over, the denominator would have a 4, and our x has a negative exponent, so it would also move to the denominator. For our part C, we have a lot of different bases there. The first thing that we do have is 3/9, which I'll write and I'll simplify in the next one. And then I'm looking at my x's. I'm going to have x to the 4 minus negative 2, y to the negative first minus 3, and then z to the negative 2 minus negative 5. From here, we're going to simplify this. And so we get 1/3 x to the 4 minus negative 2 would become 6. Y would become to the negative fourth. And then z is going to be negative 2 plus 5, or to the third. So from here, I know that in the numerator, I'm going to have x to the 6 and z to the third. In the denominator, we do have a 3. And since y is raised to a negative exponent, that would also move to the denominator. Right below this is a putting it all together table. It lists all of these exponent rules in one place for you to look at and make reference to. So you'll notice that the property's name is listed, the definition, and likewise an example for you to look at. So definitely things to make sure that you know for this class. In addition, we also have exponential forms that are going to be rational exponents. And so we are able to write the root of something raised to a power. And so we have the nth root of a to the mth power, or which is equivalent to saying the root first and the power second, which is equal to a to the m over n, where m is the power, or you can also say exponent, and n is going to be the root of that base. And so at the top of the next page, it says to simplify rational algebraic expressions, first find common factors in the numerator and denominator and reduce these factors. So the example says completely simplify the algebraic expression. Part A is 15 over 25, which I know we usually reduce by dividing both the top and the bottom by that greatest common factor. I'm going to rewrite this a little bit different. I'm going to say 15 is the same as 5 times 3, and 25 is the same as 5 times 5. And so we know that 5 in the numerator and 5 in the denominator are common factors, and so these just reduce to 1. or this simplifies to 3/5. So we usually shorthand this and can kind of look at it and simplify and reduce that down right away. But we're going to apply the same technique of finding that common factor, which you notice we're multiplying. We're not adding or subtracting. It's being multiplied in both the numerator and denominator, and then we will reduce it. So likewise for part B, if you look at the numerator and the denominator, you will see that we have x plus 1 as a common factor in both the numerator and the denominator. And so these would reduce down to 1, and we'd be left over with 2x minus 1 over x minus 7. Part C says 2x minus 7 over 4x. And for this one, we can't reduce anything. If you notice, there is an x in the numerator and an x in the denominator, but because there are other terms, like that minus 7 in the numerator, it's not a factor. So we're unable to reduce and cancel things out on that one. Part D has been extended, and if you notice, we have x plus 3 in the denominator, and we also have an x plus 3 in both of the terms in the numerator. And so what we're going to go ahead and do first is factor out that common term in the numerator. And so factoring it out, you have 4 x plus 3's in the first term, and you have 3 in the second term. So the most that we can factor out is 3. So we're going to have x plus 3 to the third. And then left over in the first term, we do have a 4 and an additional x plus 3. Then we have a minus 6. We took out all the x plus 3's in that second term. But we have a minus 6, and then we have a 2x minus 5. All over our denominator, which is x plus 3 raised to the second power. And so we have x plus 3 factor in the denominator and in the numerator. 2 of them are going to cancel with 2 of them up above. And from here we can also distribute these values, and it's a negative 6 being distributed also. So we have an x plus 3, and then in brackets we would have 4x plus 12 minus 12x plus 30. And then from here, combining our like terms, we have an x plus 3, and then we have 4x minus 12x, or negative 8x, and then we have a 12 plus 30, so plus 42. If you notice also in this factor, the negative 8x and 42, we actually have a common factor in here, and that common factor that we have would be a 2. And so you're able to divide both of these by 2, and I'm going to go ahead and make it be a negative 2. And so I'm able to pull that negative 2 out in front. We have an x plus 3, and then we're going to have a 4x minus 21. And so that would be completely factored. There's nothing else that we can factor out. And so E here, I'm going to go ahead and circle, and you'll notice that some of the examples we will circle, and we'll look at these together when we meet in person for our class.